let's get started talking about the exam review. I've got this beautiful equation sheet that you're going to be using on the exam. Let's talk about what kind of things you need to know in order to get an A++++. Okay, so chapters 18 through 20. Out of chapter 18, what do you need to know? You need to know the charge on an electron, 1.602 times 10 to the minus 19 coulombs. You need to be able to, if I give you a certain number of coulombs, you need to be able to calculate how many electrons that is and vice versa. An electron has the charge minus, and a proton has the opposite charge, plus charge. So if you have net positive charge, you're going to have protons. If you have net negative charge, you're going to have a certain number of electrons in excess. So I could ask you how many electrons are extra. If you have a negative charged object, how many net electrons are there? And you're going to divide the charge by this charge per electron. I could ask you what polarization is. What does that mean? If you have charges separated, that's polarization. Coulomb's law, F is KQ1 over KQ1 Q2 over R squared. You're going to need to know that. What is the electric field? Make sure you understand what that thing is and how to calculate some stuff with it. And field lines. So over on the equation sheet, you can see going through these equations, there's Coulomb's law there, and then the next one is the definition of the electric field. And then make sure you know that electric field lines come out of sources and go into sinks. So you get positive lines coming out of the positive charge, lines going into a negative charge. When we get into chapter 19, make sure you know the concept of electric potential energy. And we've got that there. Q times the electric field. Okay, and then electron volt, what is that? That's a unit. That's up in the chapter 18 section, but 1 electron volt is just the energy required to that an electron gains after it travels through 1 volt of potential difference. Electric potential of a point charge, make sure you know what that is. I've got it over here, KQ over R, and make sure you know what it looks like. Equipotential lines, and that's what I mean by what does it look like. So make sure you know that for like a point charge, the constant radius means constant potential. And then for capacitors, make sure you know the definition of a capacitor, how to calculate it. If I give you the area of the plates, like the kappa epsilon naught A over D, dielectric, what if they're in series, what if they're in parallel. And then the energy stored in a capacitor, 1/2 CV squared. Make sure you're able to do that. In chapter 20, current. What is current? Coulombs per second, amps. Ohm's law, V equals IR. Make sure you know resistance and resistivity. So how do you calculate the resistance of a resistor? Using its resistivity. Electric power, P equals IV. AC versus DC. Make sure you know all your RMS values of voltage and current. In chapter 21, make sure you know how to add resistors in series and parallel. What is the difference between the EMF of a battery and its terminal voltage once you hook it up? What are Kirchhoff's rules and how do you use them? And then how do capacitors behave in DC circuits? So let's go through some problems here, and what I want you to do is to do these problems and pause them after you read the problem, and then try to do it. And then if you get a little stuck, I'll tell you how to do it. So let's go on here. So let's say you've got a certain lightning bolt moving 40 coulombs of charge. Question is, how many fundamental units of charge QE is this? Oops. So pause it or whatever. Try to do this. We have the total charge is 40 coulombs. And we know that there's 1.602 times 10 to the minus 19 coulombs per electron, like that. Okay, and so if you do that, you're going to get a number, and that number is going to be a large number of electrons. And so that's what that's asking, is how many electrons are in 40 coulombs of charge. And if one has that many coulombs, then you've got that many coulombs, you divide the two. Let's say you got an amoeba here. Let's say it has 1 times 10 to the 16 protons and a net charge of 0.3 picocoulombs. How many fewer electrons are there than protons? So we know that it has a net charge of 0.3 picocoulombs. So we're going to say that 0.30 picocoulombs is the number of net protons. So we can divide that by 1.602 times 10 to the minus 19 coulombs. By the way, this pico is the same as times 10 to the minus 12 coulombs. And that's what a picocoulomb is. So you divide those two things, that's going to give you the number of protons, the number of excess protons. So if you have 1 times 10 to the 16 protons, 1 times 10 to the 16 protons minus the number of protons you calculate that are extra will tell you how many electrons are there in there. Okay, because there's if there's this many protons and that many of them are above the number of electrons, then you can calculate that from there. Okay. What about this? What is the repulsive force between two pith balls that are 8 centimeters apart and have equal charges of minus 30 nanocoulombs? So this is a Coulomb's law. F is equal to minus KQ1 Q2 over R squared. Okay, so we're going to have minus K, which is 8.99 times 10 to the 9. They both have negative 30 times 10 to the minus 9 coulombs. So I'm going to square that because we get 2 of them, and that's going to end up making that positive. And then the distance between them is, I don't know why I put a minus sign in front of that, 0.08 meters squared. They're 8 centimeters apart. And you can do that and get the calculation. All right, let's say you have 2 point charges exerting a 5 Newton force on each other. What will the force become if the distance between them is increased by a factor of 3? Okay, so pause it, resume. F is equal to KQ1 Q2 over R squared. We've got 2 point charges. You've got 5 newtons of force in this given configuration over R squared. And then let's say we change it. So we're going to have some new force. So whenever you have a problem like this, you can divide them. F is equal to, we're going to have the same KQ squared, but now our R is going to be 3R squared. So that's going to be, so let me clear this up again a little bit. So so our first force is 5 newtons, and that's going to be KQ squared over R squared, divided by our new force. We don't know what that is, but it's going to be the same KQ squared divided by the R squared, and the R squared is increased from the original R to 3R squared. So if we divide these two things, we're going to get 5 newtons over F is equal to, that's going to cancel, that's going to cancel. We're going to have 9R squared over R squared, cancel that out. So we're going to have that the force, if we bring the F back up here, we're going to have F is equal to 5/9 what it originally was, well, just 9 times smaller. So if the distance is increased by a factor of 3, we're going to decrease the force by that 3 squared, so that becomes 9. Okay, that's the 1 over R squared nature of Coulomb's law. All right, so let's say you have 2 point charges and they're placed this far apart. Where could you put a third charge so that the net force on it is 0? Pause, resume. Okay, so you got 1 charge and another charge. You got plus 5 microcoulombs and minus 3 microcoulombs, and they've got a certain separation of 0.250 meters. Okay, where could you put a third charge so that the net force on it is 0? So you could probably find a spot over here, maybe over here, somewhere in the middle. The goal here is that you want F net to equal 0. So if I put a charge somewhere here, I need it to have no net charge on it. So what I need to do is find where the net force from these two things is 0. So we're going to have F is KQ1 Q2 over R squared, and we need to add some force on it. Let me take a look at this question. This is from chapter 18. I feel like I'm missing some information here. Chapter 18. Okay, so this is Coulomb's law. Sorry, pause. If oh, I see. Okay, so it's number 25. Point charges of 5 microcoulombs and minus 3 microcoulombs are placed 0.25 meters apart. Okay, so work at a third charge be placed so that the net force on it is 0. This is not the problem I thought it was. Let's skip this one. I don't like this one because it's a little too vague. What is the magnitude and direction of an electric field that exerts 2 times 10 to the minus 5 newtons upwards on a force, upward force on a negative 1.75 microcoulomb charge? Okay, so you've got an electric field. Okay, it's pushing up somewhere, and then you put a charge in there, and then the charge experiences a force of negative 2 times 10 to the minus 5th newtons. Okay, and the question is, what is the magnitude and direction of the electric field? So we know that if the force on the negative charge, okay, so let's clear all this. So we've got a minus charge, okay, and we know that electric fields go from plus to minus, so that's our electric field lines, and we know that negative charges are attracted towards the positive side of a thing. So in this case, if our force is upwards and it's a negative charge, then the electric field has to be pointing down opposite to the direction of the force, and the force is F is equal to QE. That's the force on a charge, and so we have this force and that charge, so we can get that the electric field then is 2 times 10 to the minus 5th newtons divided by a negative 1.75 microcoulombs, and that gives us our electric field that's pointed in the opposite direction from the force. Okay, and let's say we have a positive charge Q here, and we want to sketch the electric field lines near it. Okay, go ahead and do that. And this is a source, so, and it's a point charge, so the electric fields are radially outward and the arrows point away. If this was a negative charge, the arrows would point towards it. Okay, that's what you have to know. Alright, so then this one says sketch the electric field lines in the vicinity of this conductor given the field was originally uniform. So we have a nice uniform electric field here, and then what's going to happen is if the electric field lines are going this way, they begin on positive charges and end on negative charges. So you're going to have a bunch of negative charges going over here and a bunch of positive charges going over here. So this is a conductor in an electric field, and the lines are going to come in and end on the, and this is a bad, there we go, and then they're going to go back off. And the key thing you're going to be paying attention to here is that the electric field lines end on negative charges, and that they are perpendicular to the surface when they leave. So they leave at a right angle. Okay. Then we got a kind of tricky hard one here. So you got this ball hanging in a uniform electric field. Given the charge is 1 microcoulombs, find the strength of the field. Okay, so there's 2 forces involved. So pause. 2 forces involved on this problem. You have gravity, mg, pulling down, and F is equal to QE, the force from the electric field. Okay, and then balancing those 2 forces are the X component of the tension in the rope and a Y component of the tension in the rope. okay, and then the net tension is up in that direction, T. Okay, string is 30 centimeters long, so we know that this line, so we want the opposite side over the hypotenuse, so that's the sine. So Tx is equal to T sine theta, and then Ty then is T cosine theta, and we know that T sine theta is equal to the x component of the tension is equal to, in magnitude, the electric field strength, and the y component of the tension, T cosine theta, is equal to mg, the mass of the force of gravity on this thing. Okay, so if we divide these two equations, the tension cancels out. You have sine over cosine, which is the tangent of the angle, is equal to minus QE over mg, and you can just solve for E. Okay, next. Using the symmetry and arrangement, determine the direction of the electric field at the center of the square, given that, so A and B are minus Q, C and D are plus Q, and plus Q. Okay, so for a problem like this, I'm not going to make you calculate anything, but it says, you know, you got to, the square of this thing is 5 centimeters. So what I care about is, it doesn't tell us what the charge is at Q, but it doesn't matter. Let's imagine there's nothing there, and it just asks what's going on at the center of this thing. So you're going to have, since this is a negative charge, you're going to have electric field going that direction, going that way towards the negative sign, and from the positive signs. And then the key thing is that this has a x component and a y component. From doing all that is boop, an electric field at the center that is just straight up. So make sure you can do that, and that type of thing. That's as complicated as these are going to get on the exam, is just what direction is the electric field and so on. Okay, so in chapter 19, show that the units of volt per meter and newtons per coulomb are indeed equivalent, and so that's, you have electric field is equal to force over Q, so that is newtons per coulomb, and then the electric field strength, so a newton is a kilogram kilogram meter per second squared divided coulomb, and then a volt is same thing. Shoot, there we go. Here we go. Okay, so then meter. Okay, and so what is a volt then? So you have to go back to the definition of the volt and plug that in to show that Newton per coulomb reduces also volts per meter. Yeah, it's just working out the dimensions, the dimensional analysis. So what is the strength of the electric field between two parallel conducting plates? So you've got two plates here separated by 1 centimeter, and the potential voltage between them is 1 times 10 to the 1.5 times 10 to the 4 volts. So we want to know what is the strength of the electric field between them, and that is the strength of the electric field is just the volts divided by the separation. So that's 1.5 times 10 to the 4th volts divided by 0.01 meter. Okay, clear. What charge is stored in a 180 microfarad capacitor when 120 volts is applied to it? So what Q is equal to CV. So you got 180 microfarads, which is 180 times 10 to the minus 6 farads. That's what a microfarad is. Divided by 120 volts, and that will be the charge. Sorry, times, we want the charge, times 120 volts, okay? Wait a second, what am I doing? What charge? Yeah, times 120 volts, okay. So, that, I just confuse you all. Q is equal to CV. We want to know what Q is. What is our charge? It is 180 times 10 to the minus 6 farads times 120 volts. There we go. Okay. Find the total capacitance of the combination of capacitors here. So this is two capacitors in series, and then those two sets of capacitors are in parallel. So the first thing we have to do is combine these together, and that means 1 over C total is going to be 1 over C1 plus 1 over C2. Okay, and then once you get that, then you just in parallel to 9 times 10 to the 3 volts. So the energy in a capacitor is 1/2 CV squared, and so we have 1/2 times the capacitance, 10 microfarads times 10 to the minus 6 times 9 times 10 to the 3 volts. Okay. Chapter 20. What is the current in milliamps produced by the solar cells of a pocket calculator through which 4 coulombs of charge pass in 4 hours? So the current is coulombs per second. So we have 4 coulombs divided by 4 hours times 4, well, not times 4, times 1 hour divided by 60 minutes times 1 hour divided by 60 seconds. So that'll get you coulombs per second. And then once you have coulombs per second, then that's current, and then you'll have to times 10 to the minus 3, and then that'll put it into milliamps. Okay. What current flows through the bulb of a 3-volt flashlight when its resistance is 3.6 ohms? So this is just V equals IR. So we get a 3-volt battery is equal to I, and we're going to divide that by 3.6 ohms, and that's going to give us the current in amps. What is the resistance of a 20-meter long piece of 12-gauge copper wire having a diameter of 2.05 3 millimeters? Okay, so we have a wire, really long wire. It's 20 meters long. It's 12 gauge, which means it has a diameter of 2.053 millimeters. So the resistance of this wire is going to be the density, or the resistivity of copper times 20 meters divided by the area. And since it's a circle wire, the area is pi r squared. So we're going to take d over 2 to get the radius, and then do that, and that's going to be our resistance. So we're going to have to look up or be told, like if I did this on an exam, I would tell you in the problem what the resistivity of copper is, and you could plug all that in. And so I'd recommend looking that up in your book just to practice, and then calculating what that is. So what power is supplied to the starter motor of a large truck that draws 250 amps of current from a 24-volt battery? So P is equal to IV. So we have the power is going to be 250 amps times 24 volts. Okay. We've got heavy industrial equipment using AC power has a peak voltage V0 of 679 volts. The RMS voltage, we remember, is less than the peak voltage. So we're going to take V0 and divide by the square root of 2, and if we do that, we're going to get our RMS value. So it'll be 679 volts divided by the square root of 2. So remember, our voltage is going from peak to minus peak, and then the average is somewhere in there. Okay, what is the peak power consumption of a 120 volt AC microwave that draws 10 amps? So whenever you see something like this, 120 volts AC, 120 volts AC is equal to VRMS, and it draws 10 amps RMS, 10 amps RMS current. So first thing we need to do is take 120 volts and multiply it by the square root of 2 so we can get to peak voltage, and then 10 amps times the square root of 2 to get to peak current. And the peak power consumption then is P is I0 times V0, P peak. Okay, P equals IV. Cleared everything. So there you go. Our max is I0 V0, and our average is half that. So chapter 21, what is the resistance of 10 275 ohm resistors connected in series and in parallel? So you're going to have 1, 2, 3, 4, up to 10. So the total resistance is just going to be 10 times 275 ohms of resistance, and that's going to be the total resistance of 10 in series. In parallel, 1 over R total is going to equal 1 over R1 plus 1 over R2 plus blah 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 and they are all the same R, so it's going to be, this only works because they're the same resistance, so it's going to be 10 over R, and so R total is going to equal R divided by 10 in parallel. Okay, standard automobile batteries have 6 lead-acid cells in series, so you have a battery, a battery, a battery, and so on. Blah, blah. So your total is 12 volts of EMF, but what is the EMF of an individual lead-acid cell? So since they're in series, you can just do 12 divided by 6 cells, and that'll tell you that each one is 2 volts. Okay. What is the internal resistance of an automobile battery that has an EMF? So EMF is equal to 12 volts and a terminal voltage of 15 volts. So we're going to have our terminal voltage is the EMF we have minus the voltage drop across the internal resistance. So we have 15 volts is equal to 12 volts minus 8 amps times the internal resistance R. In this type of problem, I'm going to give you an equation that, or I'll give you some A, B, C, D options, and you'll just have to choose the one that adds them up correctly. So for example, what is the potential going from point A to point B? So that is just going to be the current through that resistance. The potential difference from A to B is just I1R1, and it's minus because the current is in that direction, so the voltage drop is opposite the direction of the current. So that's that. What is the potential difference going from C to B? Going C to B is going opposite the direction of the current, so that's going to be I2R3, but it's going to be positive because the voltage drop from C to B is positive. So if I was doing my loop rule that way, I'd be going against the current, and so it would be a positive number. Apply the loop rule to A, B, C, A, F, E, D, C, B, A. So A, F, E, A, F, E, D. So they're saying go all, what is the loop rule here? So the loop rule is just adding up all the voltage drops around this thing. So we've got 18 volts, and then we're going to have, so if we go A, B, G, sorry, A, F, so we're going this way. So we're starting with minus 18 volts, and then plus, we're going to have whatever I1 is there. I1 is going to be coming back this way too. So we're going to have plus I1R4, and then as we keep going through, we're going to have I2 flowing around in that direction. So we're going to have plus I2R4, little r4, and then blah, 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 and keep going around. And then we've got another 12 volts, and so you just keep adding those things up. Okay. The duration of a photographic flash is related to an RC time constant, which is 0.1 microseconds for a certain camera. If the resistance of the flash lamp is 0.04 ohms during discharge, what is the size of the capacitor? So we're going to go to our V is equal to V0 e to the T over R, the size of the capacitance, and that is equal to RC. So we want to know what is the capacitance, so we're going to take 0.1 microseconds. We're going to divide by what am I looking for? R, 0.04 ohms, and that's going to equal the size of the capacitor. Okay.